This is to serve as an introduction to spherical mirrors. The most common type of curved mirror is the spherical mirror. There are also parabolic mirrors, which are good because they can, if you have several parallel rays, they will all reflect through a single focal point called the focus. Since parabolic mirrors are harder to make than spherical mirrors, we find that we will often use spherical mirrors in practice. So we're really going to just only focus on spherical mirrors. And as long as the spherical mirror is relatively small compared to the radius of curvature, it's a good, approximation of a perfect parabolic reflector. Okay, now you can see that there are two types of mirror shown here. There's the concave mirror and the convex mirror. The concave mirror is also known as a converging mirror, and the convex is also known as a diverging mirror. Converging because these rays that you see coming in here, this ray here is coming in, and this ray over here is reflecting inwards towards this point. They're converging to one singular point. This point here is called the focus. These light rays here on the outside that are near and parallel to the principal axes are called parallel paraxial rays. Let's go down here and put the definition in here. We have paraxial rays here. So there's your definition of paraxial rays, light rays that are parallel near to that principal axis. So I guess we should define what the principal axis is. This line right here is the principal axis. That's that line that connects the center of curvature, C, the focal point, and this point in the mirror, which we're going to label as the vertex. And I'll just label that as a V here. The principal axis is basically a straight line that is drawn from the center of curvature, C, to the midpoint of this mirror, which I labeled V for vertex. And I suppose we should also define what C is. C is that center of curvature. It's the center of a sphere. So if you imagine you were to draw a big sphere around here, a big circle, C would be the center of that circle. So it's the center of the sphere which the surface is a part of. And the next thing we should define here is this big F, which stands for the focal point. The focal point is the point where all these paraxial rays, that are really rays that are coming from an infinite distant source, and so they're coming from infinitely far, and these rays are coming in parallel to the principal axis, near to that principal axis. So these paraxial rays that when they reflect, they converge to this point right here called the focal point. That would converge if it's a concave mirror, and if it was a diverging mirror or a convex mirror, they would diverge after reflection and seem to appear to come from this point behind here called the focal point. So this is the point here at which they seem to converge here for a concave mirror, but if it's a convex mirror, they diverge from this point. And it's a point that's on that principal axis. Okay, what else do we have to define? Oh, it looks like we have this F here, that script-looking F, which is known as the focal length. The focal length, which you're going to be using in a lot of your computations, is the distance between the middle of the mirror to the focal point, or the distance from the vertex to the focal point. And there you go, the definition of focal length is that distance between the focal point and the middle of the mirror, V. Alright, what else do we have here? Oh, the vertex. And the vertex is the point that is in the middle of the mirror surface that is on the principal axis. And then we have magnification. You'll see this later when we start to construct our images and compare the image to the object. The lateral magnification is really the ratio of the image to the object lengths. This basically gives you the magnification of the mirror. And there's one other special added feature that I forgot to put into this diagram, and that has to deal with the radius of curvature. The radius of curvature is the distance from the center of curvature to the middle of the mirror, the vertex. So it's this distance right here. And that's true over here as well. You can see R is labeled. So we have R. Now something special is true for spherical mirrors, and we can see that the focal length is equal to half of the radius of curvature. And that is true. That's your first equation or relationship we know is true for a spherical mirror. Okay, so hopefully you understand the terminology with these mirrors, and so the next thing is to discuss how we can construct images.